All right. Hello, everybody. Welcome to Astronomy Days, and thank you so much for joining us to talk about the Dragonfly drone. My name is Laura Beth. I will be your host today. And to get us started, we have a question for you. So go ahead and type into the chat. If you could travel around Titan, which type of transportation would you use? Would you use a rover, helicopter, a boat, or a submarine? So type your answers into the chat and let us know why you would choose that form of transportation. And while you're thinking about that, I will go ahead and do a quick Zoom tutorial for those of you that are joining us in Zoom today, just in case you are new to the platform. So we suggest that you have the presentation in speaker view so that our guest speakers are spotlighted for you. And if the video is ever covering the slides that we share, you can go to View Options in the top of the window and choose Side-by-Side mode. We also have captions available for the program. To turn those on, you click the button that says Closed Caption at the bottom of the screen, and then choose Show Subtitle. And finally, whether you are joining us in Zoom or YouTube, we would love to hear from you. So please use the chat to ask us questions and make comments. Just remember to be a good digital citizen, so stay on topic and be respectful to everybody in the program. All right, and I'm not seeing any, I am seeing some responses now to our question. Let's see. So Eric says they would choose a submarine to see what's in those methane lakes. Jasper would choose a glider or a helicopter with human power. All right, so Jasper's looking to get some exercise, maybe? It's a human-powered glider. That does sound fun. Great responses. All right, everybody. Well, you can keep typing your answers into the chat, but I am going to go ahead and introduce our two guest speakers for today. I'm really excited. We have Jeff Qualls, a NASA and JPL Solar System Ambassador, and Dr. Jani Radebaugh, a planetary scientist and professor of geology at Brigham Young University. And just a little bit about Jani. She specializes in field studies of extreme environments of Earth that are believed to be similar to the environments on planets and moons in our solar system. She was an associate member of the radar instrument team for the Cassini mission to Saturn, and she is a member of the science team for the Dragonfly mission to Titan. So thank you both so much for being here. I'm going to go ahead and let you take over now. Jeff, you should be able to share your screen.
All right. I'll do this now. And all right, here we go. Okay, thanks and welcome everybody. Really appreciate you being here, and I hope that you've been able to enjoy some of the other great presentations that have been part of this Astronomy Days. I think we're bringing it to a close with this one. And before I begin, I just want to say I'm really happy to have Jani Radebaugh from the Dragonfly science team here helping me out. I will give sort of an introduction to the mission, and then I'll turn it over to Jani, and she can tell you everything I got wrong. So anyway, Dragonfly, as you probably know, is a mission that was approved in 2019 by NASA to go to Titan and fly a rotorcraft around Titan, and to be able to visit a large area of Titan that you couldn't get to with a rover. And it's a pretty exciting mission. It's definitely got the cool factor with it. So I'll just get going. So why do we think Titan is so important? That's where you start with this mission. Scientists have known for decades that Titan was the only moon in the whole solar system with a dense atmosphere. So that makes it pretty unique. And when we went through the Saturn system with Voyager 1 back in the early 80s, scientists were so excited about what they could learn from Titan that they decided to divert the the Voyager 1 spacecraft past Titan rather than send it on to Uranus and Neptune as Voyager 2 did. So they really wanted to check it out and see what they could learn about that atmosphere. And what they got back were pictures like this that were both tantalizing and disappointing because they really didn't show much because that atmosphere is so dense and really you just can't see through it in natural light. And Cassini didn't have instruments that could go beneath the cloud layers. So they learned enough to spur them on to what other kinds of missions they could send there to learn more of what they wanted to know. So almost as soon as Voyager was out of the Saturn system, the talks began about what kind of mission can we send to learn more about the whole Saturn system, but definitely about Titan. And those talks led to the Cassini mission, which went into orbit around Saturn and stayed there for, I think, 15 years. And it's one of the greatest missions of scientific exploration NASA's ever sent. And Jani was on that science team, too. So as far as Titan is concerned, and why we would want to go there, we don't know enough about how life came about on our own planet. We want to know how it came about, and Titan happens to be sort of a laboratory where similar processes are going on in the chemistry that is there as what was happening on Earth in its very early days. But we can no longer find out by studying things on Earth enough of what we want to know about what was going on in those early days. So Titan is a perfect place to visit because it is so much like Earth was in its early history. Titan is the second largest moon in the whole solar system. It only comes behind Jupiter's moon Ganymede. It's larger than our own moon, and it's even larger than the planet Mercury. And it's about 50-50 in water, ice, and rock and metal as far as what it's composed of. And really intriguingly, methane there can exist as a gas, a solid, or a liquid, as you'll see in some slides that are to come. And other organics are also present there that contain various forms of combinations of carbon and hydrogen, and they are perfect ingredients for the chemistry of life. As I said, it has a thick atmosphere, and it's mostly composed of nitrogen, as is Earth's atmosphere. However, what remains in Earth's atmosphere, there's a lot of oxygen. In Titan, the second most prevalent element is methane. And so there's only a little bit there, but there's enough to make things interesting. The pressure there is about 1.5 times that of Earth, and the density is 4 times that of Earth. So guess what? That makes it a really good place to fly things. It's really good for creating lift. The temperature is 94 degrees Kelvin, which is minus 290 degrees Fahrenheit. And the water ice there is frozen solid like rock on Earth. All right, as part of the Cassini mission, they sent a tag-along probe called Huygens, which landed on Titan back in 2005. And to date, it's still the only landing craft we've ever sent to another moon. It descended to the moon's surface, and the atmosphere is so thick there, and the gravity is so slight that using a parachute, it took about 2.5 hours to descend. And it took some great pictures of some magnificent landscapes there, as you can see on the right side of this slide. And we found out that there were like rivers there, as you can see on the left side of this slide. Those are river channels, but they were carved out by methane, not water, liquid methane. And on the right side, once Huygens got down to the surface, it took a photo, and what you see there looks like a field of rocks, but actually that's a field of pieces of water ice that look like rocks. So the probe didn't last but a few hours on the surface. It was only battery powered. So we learned a lot during the descent on the parachute, and then once we got there, we had a few hours worth of science that we were able to get. So again, kind of tantalizing, but we want to go there and do science for a lot longer than a few hours. So these are pictures of Titan using infrared light. So you can see much more through the clouds than you could using natural light. And we also used the radar image, which Jani was a part of that radar team, to get some pretty incredible images of lakes and seas that exist on Titan. And they look a lot like lakes and seas on Earth, but again, they're filled with methane. And an interesting thing is that there's a weather cycle on Titan that involves methane rain. And I have heard this rain described that it falls in rather big drops, and it falls with about the speed of snow on Earth. So if you just try to imagine that, it must be a strange sight to see these big globules of methane raining out of the sky in slow motion. So yeah. Another thing that we discovered about Titan is that there are lots of dunes there made up of organic sand. And Jani loves to talk about sand, so I believe you're going to hear her do that in just a few minutes. There's a lot of things we can learn about sand, and I know she wishes she could have a handful of that stuff to analyze right now. That's an artist's conception of what the dunes look like on Titan. And then I'm no organic chemist, so I'm not going to get too deep in the weeds here with these slides about organic chemistry. But the bottom line is that there's methane in the atmosphere of Titan, and the sun breaks it apart, and the molecules reform into more complex organic forms like benzene, propane, acetylene, and that makes Titan a very interesting place because there's all that organic stuff there. As I said, it's a laboratory, and there's plenty of energy for sunlight and photochemistry, all that organic material on the surface, and liquids, both water and methane. Now, the liquid water actually exist in what they believe is a subsurface ocean there, like on some of the other moons. So there is liquid water there, and there's an opportunity for life to exist down there, life as we know it here on Earth. And scientists also think that life as we don't know it might exist up there in the minus 290 degree temperatures on the surface, with all that organic chemistry going on. I want to read you a quote from the principal investigator of Dragonfly. She has said that Titan is doing complex organic chemistry experiments and has been doing so for hundreds of millions of years. And what we want to do with Dragonfly is we want to go there and pick up the results of these experiments. And I think that's a nice way to look at, the ultimate goal for Dragonfly. All right, so since Cassini and Huygens showed us what was really down there, there have been a lot of proposals for how we should explore Titan next, and I'm just going to give you a sampling of those in the next few slides. This one was called Titan Saturn Mission System, and it's really my kind of mission because I believe we should be spending a lot more money on planetary exploration. And basically, I think we should have a whole fleet of spacecraft heading out toward the outer solar system to study all those planets and moons. But I'm not in charge. But this one was a very ambitious, complex, and expensive mission that was going to involve an orbiter, uh, a lander that would land in one of the lakes or seas, and it was also going to have a balloon that would drift around in the atmosphere of Titan. And one of the things about that orbiter was, I mean, it just keeps getting more elaborate the more you read about it. Before it settled into orbit of Titan, it was going to orbit Saturn and do several flybys of Enceladus, which, as I spoke of yesterday in the talk I gave about Brewy, is a rather interesting place itself. And then once it did those flybys of Enceladus, it would come back, orbit Titan, and drop the lander and the balloon. Well, really complex, really expensive. I think they estimated at the time that it was going to cost like $2.5 billion, and I bet it would have ended up being double that. So very interesting ideas and concepts, but just wasn't going to fly. This one here is sort of a budget mission, Titan Mare Explorer, that was going to land in one of the lakes or seas and float around for 6 months or so using nuclear power, to keep it going. And that one was, as I said, on the cheap side, about $500 million, which in terms of NASA missions is cheap. I know it may not sound cheap, but it was. And finally, this is an early proposed drone mission, Aviator, which I believe Jani was in on the conceptualizing of for this one too. It was more of a drone plane, and I think they decided to go more in the rotorcraft direction because the rotorcraft technology has really been progressing rapidly over the last decade or so. And I think that there's more stability and, more redundancy if anything goes wrong. But this particular thing was supposed to possibly stay in the air flying for up to a year at a time, which I think that might have been hard to pull off, but who knows, because they're not going to do it. But anyway, they arrived at the idea of Dragonfly, which is really a dual quadcopter, or you might call it an octocopter, because it's got 4 sets of two rotors each, which provides a little bit of redundancy because you can lose a rotor. You can lose at least one rotor and still keep going. And I've read that if you could possibly lose 3, as long as they were on different corners of the craft, and it could still keep going. So I'm going to show you a little video of the Dragonfly landing sequence right now. All right. As I said, it definitely has the cool factor going for it. So flying on Titan is actually going to be easier than flying on Earth because of that thick atmosphere, but also because the gravity on Titan is only 14% of what we have here, similar to what we have on the moon. So it's just easier to create lift. The atmosphere is 4 times as dense as what we have on Earth, and it's colder. And I believe the cold also helps in flying. And again, just the advances that have been made in drone technology and also in autonomous flight have really helped this mission to come to be. Because on as far away as Titan is, the radio signal one way from Earth to Titan is well over an hour, and so it's got to be able to fly on its own. I mean, it will do reconnaissance flights so that it can, map the areas where it might go, and then the people on the ground can sort of plot out a course for it. But it still has to fly itself ultimately. And in the landing sequence you just saw, it has to fly itself to its first landing site. So it has to be able to recognize places that would be dangerous to land. So the autonomous flight is kind of, revolutionary in terms of being able to let this thing fly itself around. Okay, so finally, the goals of this mission are to analyze that organic chemistry, do measurements of atmospheric conditions. It's basically going to be able to it's going to be like a little weather station wherever it lands to give the local weather of Titan. And also, it's going to be able, it's not on this slide, but it will be able to record seismic activity in local areas where it lands. So that's pretty interesting. It's going to investigate places where organics mix with water, and those might be like impact sites from crater impacts, meteor impacts, and also places where maybe some cryovolcanic activity is taking place, where the water ice has melted and mixed with that organic stuff. And it will search for evidence of life. It will do all those things with a suite of scientific instruments. It will have several different cameras that will take photos and videos forward and downward of the drone, so they can map areas for future flight. There will be, and that includes panoramas that they will take, and also they'll have a microscopic imager to really get fine, detailed images of the sand beneath the lander. There are 2 different kinds of spectrometers on Dragonfly. There's a mass spectrometer that will actually ingest sand up through the legs and will identify the composition and look for organic chemicals. And there's also a gamma ray and neutron spectrometer that will remotely determine composition on the ground. And then there's that meteorological station that also has a geophone for measuring seismic activity. So this little drone will be able to do a lot and tell us a lot about Titan. So I'm going to show you one more video and get out of the way and let Jani take over.
Saturn's largest moon, Titan, has a thick atmosphere and a frozen surface rich in organic molecules. In 2034, a NASA mission called Dragonfly will arrive at Titan and study its chemical makeup. Dragonfly is a rotorcraft designed to visit multiple sites across the moon's varied terrain. At each new landing site on Titan's surface, Dragonfly uses a pulsed neutron generator and onboard gamma ray sensor to detect key elements such as carbon and hydrogen in organic materials or oxygen in water ice. Dragonfly determines if there are well-defined layers of these materials just below the lander. For a closer inspection, Dragonfly uses its drill to generate tailings from Titan's hard, frozen surface. These surface samples can then be ingested through the pneumatic system, carried with Titan air into the chilled sample lines and to the sample collection carousel. One of the carousel sample cups is placed in a pneumatic port. The cup captures the surface material from the cold air stream and transfers it to the chemical laboratory for measurement. Pulses from a laser release large organic molecules from the surface sample for analysis in the mass spectrometer. The mass spectrometer sorts molecules by mass and measures diagnostic fragments that tell Dragonfly the kinds of chemical components that are present in the surface and whether there are molecules of prebiotic interest. For those potential prebiotic samples, a new cup is placed into an oven and heated to release molecules into a gas chromatograph, where they are sorted for size and type before entering the mass spectrometer. This advanced separation of organic components includes isolating molecules with the same formula but different chiral arrangements, or handedness. Having a preference for one-handedness over another is a key biosignature for life on Earth. When the chemical analysis is complete, Dragonfly may choose to take another surface sample or find a new location on Titan to investigate. Saturn.
Okay, so I'm going to conclude now, but I want to leave you with one thought. You all know about the rovers that we've sent to Mars, and they have done a lot of great scientific work there, but they can't go very far very fast. Curiosity has been on Mars for 10 years, and it has covered about 16 miles. Dragonfly could do that in one flight. So it's going to be able to cover lots of different areas. It's going to have multiple sites that can do science in, and it will just increase the coverage we can have by leaps and bounds over what we can do with a rover. So it's a really exciting mission, and right now it's scheduled to launch in 2027, arrive at Titan in 2034. And so something to look forward to in the future. So I'm going to turn it over to my friend Jani Radebaugh, and I will advance the slides as you wish. Jani, take it over.
Okay, thank you so much, Eric. I'm super happy to be here. And I just wanted to add that I know Jeff because he and I, and also somebody else who's online, Eric, all met each other at an event called Space Fest. And this is something that, used to be about every year. COVID has kind of messed with it a bit, but this is a chance to go and meet and hear from Apollo astronauts and other scientists. And I mean, in many ways, it's similar to what you have going on with astronomy days, where you gather together and hear about science and what's going on in space. And so you can find some of your most kindred spirits at these kinds of events. So I hope you're taking advantage of all the opportunities associated with this. So as Jeff says, I'm a planetary scientist, and I've been working with Titan since I was a postdoc. And this was in about 2005, and started to work on the Cassini mission just as it arrived at Saturn. I got very lucky to do that. At the time, a lot of my friends were at the University of Arizona with me, and they were also working on Titan and thinking about those problems. We got to know each other really well, went on some field trips together and did research together. And then a couple of them headed off and started this mission up. It's so exciting. And so they pulled me in to be involved as well. And it's just been a big adventure so far. You can go ahead. Yeah. So what can we learn about Titan from Dragonfly? I think that's maybe mine. Let's go to the next slide here. And I just want to kind of think about what you would see if you were flying over Titan in Dragonfly, and if you were on the ground, what you would be able to learn. So first of all, let's look from the air. And all we have right now for the surface of Titan is some radar images. And Jeff showed a few of these. We have to use radar to see through the atmosphere because it's thick and hazy, and you can't see through the atmosphere and the visible. So we use radar. We have some radar pictures on the Earth as well. And if you look at them, you'll notice all the water bodies on the Earth in radar are dark in color because they're really smooth. The radar signal hits the surface and then bounces off in the other direction, doesn't come back to the instrument, and so everything just looks dark. And so that's true as you look here at these methane lakes. You can see other bright features. If it's bright, it's usually rough or rugged, and that signal makes it back to the spacecraft to show up as bright. And so all the things that are rugged or have cobbles on the surface you see as bright. And so in the lower left corner, that one of river channels, can you believe those river channels on Titan? They look a lot like on Earth, and the other one in the lower right corner. And that's just because of that methane rainfall and erosion all across the surface. And we think if we were on the ground, we probably would see cobbles, but we don't know really exactly what the color would be like, or how many cobbles there would be. Is it mixed with sand? Are these on big hills? We just don't know the answers to those. And so if we're flying over these landscapes with Dragonfly, we would be able to see those things and understand to what degree did this progress, this surface, just like on the Earth, and would it be very Earth-like if we were there? Next slide. Here's a close-up of some of these things. Those river channels, as you can see, are next to a big round feature on the left. This is a large impact crater. This one is, a few hundred miles across. It's really quite big and is rough and rugged. And so, as Jeff was mentioning, where you have impact craters, that would excavate all the way down to where we have water ice layers in the lithosphere of Titan. And it might melt those materials. You'd have kind of a sheet of melt sitting at the bottom of the crater. And that would be able to interact with all the organics that are being made in the atmosphere and settling to the surface. So we have those key ingredients that are just right: liquid water and organics. We even can add in a liquid methane, and then energy from sunlight, and maybe even like hydrothermal energy if you're right at the site of an impact as it happens. And so those are the kinds of places we want to go and visit with Dragonfly. Next slide. As Jeff mentioned, there are lots and lots of these long, dark streaks all across the surface, and these are sand dunes. Again, if you were to look at sand dunes in radar images on the Earth, they would also look dark, and it's because they're smooth to, they don't have anything that's like 3 centimeters. All the particles are much smaller than that. And radar images are usually around 2 or 3 centimeters for Titan and for the Earth. And so what we see are oh, hey, there's just lots and lots of sand. It's all parallel to each other. This kind of sand dune is like what we would see on the Earth in a sand sea. We actually have regions on the Earth called sand seas. It's pretty neat. Lots and lots of sand is collected over the years. It's been eroded out of the mountains, especially like in northern Africa and in Arabia and southern Africa and Australia, and has made big seas of sand. Next slide. There's a question about the visibility on the surface. And that's interesting. You could kind of get a sense of that as you saw the Huygens images. We were hoping that there would just be haze high up in the atmosphere and be kind of clear down low, but it wasn't. There was kind of haze all the way to the surface. And so it would be kind of like, foggy or a hazy day, like lots of atmospheric pollution looking off into the distance. You maybe be able to see a couple of kilometers, we hope. And there also was a question about how big Dragonfly is. It turns out Dragonfly is going to be about the size of a Mini Cooper. So it's a lot bigger than I ever expected it to be and that you might have thought. But because we can fly so easily across Titan, we can have a very big, lander that also has rotorcraft relocatability. And that's what's really powerful about Dragonfly. Here's a picture where we did look down through the atmosphere, kind of in, back one. Oh yeah, right here, I guess. Yeah, maybe back one more before that. Okay, good, thanks. So this one is where we have lots and lots of brown features on the surface. We're actually able to see down to the surface. This isn't what your eye would see. We're falsely coloring different landscapes according to what they're made of. And all the brown or orange materials you see here are sand dunes. So this is a huge portion of Titan. It's covering something like 25% of the surface. And then there are other regions you can see kind of blue and purple. Those are organics, and maybe where the purples are mixed with water ice. And so it's a really interesting landscape dominated by dunes. Next one. If you have sand dunes, then you have to have sand. And so what in the world is the sand on Titan? How could you have sand? When we think of sand on the Earth, we typically think of quartz sand. And that's what you'd find if you go out to the beach in California, or you go out to some sand dunes in the middle of the desert. But keep in mind that you could also go somewhere like the Bahamas or Hawaii, And the sand that you find there is not quartz sand. It's white and beautiful, and it's made of shells, and it's also made of other sort of concretions of calcium carbonate that have rolled around and formed in those shallow shoals as a result of chemical interactions between the atmosphere and the ocean water. And so we don't have to think of sand as being made of quartz. It could be made of other kinds of things. It just means it's fine enough to be moved around by wind. And so here's a sliver of, actually, these are all quartz sands: Australia, Namibia, Egypt, and the United Arab Emirates. Sands that I've collected. I love to collect these things and just look at how different they are, because when you're out in the field, you say, oh, there's some sand and it's sand colored, and you get it back to your house and you're like, wow, this sand is a very different color than the other sand that I collected from somewhere else. And so we do like to use color and think about what color tells us about what it's made of, but also you can have a range of possibilities. In the lower left corner, you can see a picture of bagnal dunes from Mars. And look at this sand. It's actually really dark in color, kind of a gray. It's because sand on Mars is made of basalt. And that's like lava that's flowed out across the surface and then broken up by water, by wind, back when water was active on Mars's surface. Or maybe it exploded out of a volcano and made little granules. And then those are able to be moved around by wind. So we kind of want to think about what Titan sand could be made of. And remember, we said there's lots of organics everywhere, made up in the atmosphere. It's kind of settled down to the surface, either as like a snow or maybe as an even finer powder that's made into a layer, and that gets eroded by methane into lots of different sizes. And the sand size ones are blown into dunes. We think they're kind of dark in color too, based on some other of that infrared imaging that we saw. Okay, next slide. And again, just to remind us that the dunes are a lot like big dunes we see on the Earth. They're even the same size. This tells us that the atmospheres of Titan and Earth are really similar. Remember, Jeff said 1.5 times the pressure. So you'd be able to exist there even without a spacesuit. Although you would have to have, well, without a pressure suit, you'd have to have a spacesuit because it's really, really cold. You can't have anything exposed. It will just freeze immediately. But you don't have to have a pressure suit, and that's pretty huge for human exploration. Titan's really far away. We're not thinking about sending humans there, but we could eventually do that. So here's some dunes in Egypt, and notice that they're kind of long and parallel to each other. They're straight. They're pretty big. They're like about 0.5 mile across. And that's the same for the dunes on Titan. Okay, next picture. Again, just to remind you that the dunes on Earth in radar look a lot like the dunes on Titan. So this picture on the lower left is dunes of Egypt from radar. But we have a lot more detail from our Earth radar pictures than from Titan, because the atmosphere is really thick and extended on Titan. We couldn't orbit very close. And so our pictures are not very good resolution, but enough for us to see the dunes and see how they interact with landscapes. Next picture. So we've gone out to do some field work on deserts on the Earth, just to better understand what the conditions are like there and compare them with Titan. So here we are in the Great Sand Sea of Egypt, similar to where we took that radar picture and the other linear dune pictures from in the previous couple of slides. And here we're walking up and over a sand dune that's kind of light tan in color. These are made of quartz. There's a layer underneath that's different kind of material, and we wanted to know what the relationship between the sand dunes and that layer is like. And you can see in this kind of radargram sitting up on the top, we pull an instrument over the sand and it sends a radar signal into the subsurface. Different radar. It's still the same wavelength, but not from orbit. It's from the ground. This is ground penetrating radar. And you can kind of see a horizontal line that's exactly where that boundary is between the sand dunes and the subsurface. And then you see the sand dune layers kind of inclined upward. And that kind of shows how the sand moves down dunes. It sort of avalanches down, making these inclined slip faces. Next slide. We've also visited the Namib Sansi. This is in Southwest Africa, and it's a good analog for Titan sand seas. Notice all of the dunes here. Again, these are like 1 mile across. They're very big. Up to a couple 100 miles long if you string them all together. Next slide. And so we did a flight over the top. And it's interesting, this was kind of before Dragonfly, but this is what we do as geologists. Oh, I need to see it from overhead. I got to see what's going on. What's the relationship can I see all those dunes together? And yeah, you can see all those lines off into the horizon, and then a big mountain that's kind of jutting up in between the sand dunes. Notice the dunes are kind of shifting around that island of rock, and the wind it's almost like moving water in a stream, and how it kind of moves around and then recombines on the other side. Moving sand with air is kind of similar to moving sand with water. Next slide. Here's another picture from the air. We also started to notice these landscapes in between the dunes. What is the interdune material like? And what do you think it's made of here? Could you make a prediction? If you look at this, it's white in color. It's going to be either snow or salt, right? And here we are in Namibia, so we've got to go with salt in this case. And sure enough, lots of channels flow under the dunes, and they stop in this location, just empty all of their liquids here and eventually evaporate away to leave salts. Next slide. And so, yeah, we can see what that looks like from the ground. This is my student Clay, and he's walking around on some salts and some clays, and seeing what the relationship is like here. Oh, there's some water that flows out across those regions. Would we see something like this from the ground with Dragonfly? I predict we will. So we might see these kind of evaporite surfaces, but they might be very different. Not like salts we're used to, but organic salts. What would those be like? We're in a whole different realm of materials that we don't quite understand. We don't think we're going to see the vegetation and the wood left over. That would be amazing. It would be really great, but maybe some other blocks and obstacles that would get in the way. Next slide. Okay, so we also went to some of the bigger dunes in the interior and said, what can we learn from studying these up close? And so we dragged that ground penetrating radar up and over the dunes. It took us all day just to do one. And next slide. Here we are pushing and pulling. And next one, and we ended up getting another radar gram out of that. And this is penetrating something like 30 feet down into the dunes, which is pretty good. And you can see there's all these kind of scoop-looking textures and swoopiness to the layers underneath. And they're not just straight and flat. If they were, that would be just like, oh, the sand's just coming up and over, up and over. But the swoopiness tells us the sand's actually going down the long axis of the dune. And that's really useful because it must be wind that's transporting the sand down the dunes. And so wind is sort of roughly blowing down the dunes. And so the dunes can almost act like weather vanes for us because we don't have these landed weather stations on the surface of Titan. Now we can use the dunes to help us understand what the winds are doing on the surface. Next slide. So yeah, as you look at a picture like this is a mosaic with a couple of different radar images. And just look how much sand there is. All of those stripes are sand dunes over hundreds and hundreds of kilometers across the surface. And as we look at this, we can start to overprint sand movement directions. It's all going from the left to the right. Notice how it's kind of going around those bright features. Those are obstacles in the way of the sand dunes, just like we saw in Namibia. And now we understand sand movement and it's sort of like wind direction across Titan. Next slide. Okay, we can actually find dunes in other places on Earth that are not quite so straightforward, like these here. This is in the United Arab Emirates, in the Arabian Rub al Khali Desert. And this image is an aster image. They process them really beautifully so that the difference between the dunes and the interdunes shows up very well here. Your eye wouldn't quite see the blue in color, but we can stretch it just a little bit so that we can tell the difference. And what you notice is, the stuff underneath the dunes is very different from what's on top. And what would you guess as you're looking again at those bright colors? More salts here? Yeah, so we think that fluids are really important in some dune areas. And in particular here, there's fluids in the subsurface and they've grabbed onto the sand and enabled it to just sort of grow really big. So these are mega dunes that form because they're constrained by the pools of water, in this case, helping them. And could we see something like that on Titan? Next slide. So here's an example of one of those dunes that were kind of near the border with Oman. Can you see that border fence over there? So this is on the far eastern boundary of the United Arab Emirates looking into Oman. And again, you can see those evaporite textures, the salts. And the other kinds of things that have evaporated away once the water has left it. Next slide. And here's an example of how big these dunes can grow. Look how tall this is. This is a mountain of sand. And I'm also just so impressed at the engineering. They just build roads right through the dunes so that they can go and recreate, and they can also have hotels out on them. If you ever get a chance to visit these dunes in the United Arab Emirates, it's pretty easy to get to them, and they're so spectacular and beautiful. In fact, you've seen them in the Star Wars movies. This is where Jakku was filmed, is right next to one of these dunes, probably very close to one of these roads that we're driving on. Next slide. Okay, so yeah, if we've got these big dunes, and we've got liquids nearby, on Earth, this is important because this is a really inhospitable area. You don't see vegetation anywhere else. You don't see palm trees or anything. This area is really pretty hyper arid and is really hot. But we have these pools of water that kind of sneak in from underground. And you can see a kind of regular spacing to the mounds behind us. Those are actually algal mounds, algal mats, and other kinds of things. There's life in the interdunes here. So we want to look for something similar on Titan. Could there be like methane fluid between the dunes? And the methane might help enable there to be life in those locations, even though you might not expect it in a desert area. And these are all my students having a really good time taking pictures and video. I think I saw a question about avalanches on the dunes. Yeah, there are avalanches. In fact, pretty regularly, that space that they're sitting on just avalanches down, but it's just bit by bit. So there's no danger of kind of like falling over very quickly. Next slide. Okay, I just want to wrap up with a couple of things just to build on what Jeff said. It is now in design. So the engineering is moving forward. This year, we're in review for the engineering. We've got to pass that review in November. NASA will be very careful about the review, and they want to make sure it's going to work. So that once it passes a review, then we can start building the spacecraft and get it ready to go. Here's one of the blades. Remember, there's one on each side of each of those rotors. And so this is really pretty big. It has all kinds of instruments on board, and we can't bring anything back with us, so we've got to study it all on board. But we're getting so good at that. As you look at the Mars missions, we've been able to tell a lot about what's going on the surface just from being there in person or with the spacecraft. And so that's what we plan to do. Next slide. And I'm just most excited about the images, believe it or not. Well, I guess, and the mass spectrometer. I'm excited about the whole thing. But the images, then I get my pictures of the sand dunes from different scales. And here on the left, you're seeing the dunes on Mars from a variety of scales. They have it on Mars, so I want it for Titan. And we'd be able to get that and get this handful of sand, like Jeff said, virtually, so that we can tell what's happened in the area. Because a lot has gone into make sand. As you know, on the Earth, it's got to be broken down, it's got to be moved to that place, and it kind of tells you a record of everything. The sand I'm holding in my hands on the right was really pretty neat. It's from a beach in Kauai called the Glass Sand Beach. I was like, Glass Sand Beach, how could that be? And you go and you pick it up, and yeah, it's all glass sand. And I thought to myself, wait a minute. And I wandered around the corner, and there's a big trash dump and lots of glass bottles. And so the sand told me about what was going on around the corner. And that's exactly what we think we'll get for Titan. Next slide. And Jeff kind of went over this already. The mass spectrometer will reveal the materials and the compounds. And then next slide. Really, it's going to offer the answers to some of these questions. What makes a planet or a moon habitable? What processes led to the development of life? And has life developed elsewhere in our solar system? And so we'll launch in 2027. We found out we can go atop a heavy lift launch vehicle. That could be one of 3 that include a SpaceX Falcon Heavy, but we don't know if it's that one yet. But then we'll be able to arrive by 2034. And you think, oh, that's so far away, but for the outer solar system, that's going to come right up before we know it. So it's an exciting time to be able to be studying it. Okay, thank you. I think we see some questions in there, but we can take some others if we have a few minutes.
Yeah, we still have, we've got about 10 minutes. We can, yeah. So most of the questions in the chat you have answered in some way, but we do have a little list of some. And Ken is elaborating on one of those questions. So how will it sample liquids? Because yes, it will sample liquids, as some of you asked.
As I understand it, there are two modes of the mass spectrometer, closed source and open source mode. And I think that one is better for solid and one is better for liquid. And I forget which is which. I'm trying to slowly learn about these details. But the way the spacecraft works is that there are drills in the legs. And so they drill into the subsurface and then draw that material up. And so also there will be a little bit of, like a straw or something to help draw up the liquid into the body of the mass spectrometer. You have to change the mode. And so we've got to try to figure out, is it wet or is it dry, or, which one is it, and get a better sense of what's happening. So we're working on that now.
Right. And so when you say change the mode, is that something that that Dragonfly will do on its own? Like it will be able to sense the material, or will you be somehow like communicating with Dragonfly?
That's a good question. I am not sure the answer to it. I feel like we need to switch it, but it would also make sense to build some autonomy in there so that when it knows, it can switch and do the right thing.
And speaking of autonomy, Eric asked earlier, what's the required level of autonomy for the drone? Will it navigate by radar or visual?
It will navigate by visual. I'm forgetting actually if there is a landing radar. There must be an additional landing radar. But we can also use primarily images to kind of understand the landscape. The hardest landing is going to be the first one because it just comes out of that shell, as you saw in the video, and flies across the landscape and finds somewhere and lands. And the communication time from Titan to Earth is something like 90 minutes. So it's not really long enough for us to be able to keep it flying and decide where to land. It needs to be able to land safely by itself first. So there'll be a decent level of autonomy to be able to do that. But beyond that, once we've landed, we'll pick up and we'll fly and scout and then come back to where we know it's safe. And once we've scouted, we can look at that location. The next time we do a leapfrog. So before we go to the next spot, we overfly a new spot and then come back to this one. So we're always doing this leapfrog technology to get from one place to the other and know where it's best to go. And it looks like each of our leaps are going to be something like 10 kilometers. So this is like already well above what we can do with the rovers in just a single flight to get to the next spot. So if we last, like we hope, 3 years, then we'll be able to fly many tens of kilometers to new locations across, we'll stay in the equatorial regions, but across all of those areas.
LB, I wanted to add something about that first landing. The Dragonfly will separate, from what I read, at about 4,000 feet up. So it's going to have to be able to see what's below it and make some decisions about a safe landing site. Yeah.
And Ken also just asked about the antenna, just asking where it was. And I just wanted to point out, in case you're watching on YouTube, Jani said that it's a round dish that will sit on top of the rover and can lift up and move. And so we had a lot of questions about kind of like the dangers that Dragonfly will face on Titan. So what are the risks to Dragonfly? Are there storms on Titan? And then like, what is it gonna do? How will that affect Dragonfly? So can you speak to that?
Yeah, Jeff, do you want to take any? I'm happy.
You probably know better about the weather patterns on Titan than I do, so I'll let you take that.
Okay, so because of where Titan is in its orbit, it's got a very cold atmosphere and everything is thick and dense. And so things are really pretty slow motion on Titan. On Earth, we kind of say if you lived on Titan and looked at Earth, you'd say there's no way life lives there. It's way too hot and there's a magma ocean and everything happens too fast. You couldn't live there. So you kind of think in the opposite direction, say, okay, we'll slow everything down. We think we could build some thunderstorms and other kinds of storms, but they'd be pretty rare and they also wouldn't be very energetic. Mm-hmm. And so we think based on the stability of this rotorcraft, we would really be able to get a lot of, we'd be able to handle a lot of these things that come up. Winds shouldn't be more than like 10 to 15 meters a second, and that's really not very high for if you think in terms of Earth and other rotorcraft. One thing we do want to think about is, well, are there going to be mountains in the way? Are you going to land on a steep slope? right now we want to aim for landing on anything less than 10 degrees of a slope. Okay, well, you can get above 10 degrees pretty easily, even on the sand dunes. We don't want to land on a sand dune. We want to land by them. And we'll have to just choose carefully where to land, and just to protect this lander and be able to use it for lots of different other places. Mm-hmm. But also, it should be noted that even the mountains and those other features that we saw in Titan, they're all kind of subdued in height. They're made of water ice, which doesn't support really high and rugged terrains, and so they're kind of muted all across the terrain. And so we think we'll be able to see them and avoid them.
Mm-hmm. And Glenn also had a question about, some of the dangers, the risks to Dragonfly. So how will you keep the mechanical parts from freezing to each other and stopping the rotors from spinning?
Yeah, that is definitely something to make sure. Can the rotors operate in 90 degrees above absolute zero? And we've got the technology to be able to do that. And so that should be okay. There's some other instrument things that need to be warm. So the lucky thing is that we've got a radioactive power source sitting on the back. And this is decaying over time. It's generating waste heat. It's being used to charge up the battery for the aircraft. But we can also use that heat to keep the parts warm that need to stay warm, and then build a wall to kind of wall everything off to keep things that we want to keep cold away from that warm part. And so you can kind of have what you need.
Mm-hmm. And Ken is asking, what is the projected lifetime of Dragonfly?
It's the primary mission, I think, and correct me if I'm wrong, Jani, is 2.5 years, but I'm sure that they're hoping for an extended mission to come after that. Yeah.
That's right.
And this is going to have to be our last question. Will Dragonfly take a photo of Saturn from Titan?
Can we see it through the atmosphere, Jani? I'm not even sure.
I'm not completely sure either. I think we will try, is my guess. If we can look upward. I don't know if we plan on trying to make cameras that can look up, or maybe just out across if it's low on the horizon. I think it'll be difficult, but it would also be really instructive about the atmosphere. So hopefully we'll try.
Right. And there will definitely be cameras to take some nice close-ups of the sand, right? Because that's like your baby is the little sand.
Sure.
Yeah. Well, everyone, thank you so much for joining us today. And of course, Jani and Jeff, greatly appreciate both of y'all sharing your expertise with us. This was really exciting, and we're going to have to say goodbye, but I do want to remind everyone that we have Astronomy Days t-shirts for sale. If you are a Friends of the Museum member, you can get 10% off of those shirts or hoodies. I also want to say thank you to our sponsors, the North Carolina Space Grant and Pepsi. And of course, if you are a Friends of the Museum member, thank you so much for supporting our programs and our research every single day. We do have one last program to wrap up Astronomy Days. It is the Lego Show and Tell, and that one is only going to be in Zoom. So it should be a blast. And thank you everyone for joining. Have a great day.
Thanks everyone, and thank you, Jani.
Oh yeah, thank you so much. It was so fun.
Bye-bye.